the thermodynamic properties also, you can also think of like specifying temperature of the system, we can specify the pressure, and as I told, we can specify volume. Then we can describe chemical composition in terms of CaCbCc, which is basically concentration, which is like moles per unit volume, or in terms of Na, Nb and C, which is nothing but mole number. Please note that here this is something, it's a food for thought basically, you can try to understand this. These are all extensive properties. On the other hand, the properties that we are describing here, like temperature T, then pressure P, these are all intensive. Similarly, chemical composition in terms of, so if I tell in terms of C, where C denotes, it's like, you know, Ca, is it like moles of A per unit volume, right? So in that case, your Ca, so CaCbCc gets an intensive property. On the other hand, if I would have told Na means N1 moles of A, that's like a mole number, then it's an extensive. It is additive. It depends on the extent of the system, but here it is an intensive, right? So this is something that you should be very careful about. So we can describe a system in terms of intensive and extensive properties, but you will see that describing in terms of extensive properties has its own advantage somewhere, and you will see that there is a relation between them, and these conjugate relations and all these things will be discussed. Now we know that what are the different thermodynamic processes, right? We have already described some of these processes like heat input, so transfer of heat from or to the system or from the system, right? We are extracting heat from the system, or transfer of mechanical work again to the system or from the system again. Another work is like transfer of chemical work to or from the system, right? So these are possible. Now think of this. Now what type of systems are possible? Now I am basically classifying the systems, right? This is something very important, because if I can classify, I can also modify the first law or the differential form of the first law to take care of which will basically according to the nature of the system, right? So for example, if I take a glass container which contains some water at room temperature and pressure, and it is covered with a green lid, right? It is covered with a green lid, right? There is a green lid and it's a glass container, it contains some water, it also contains some air, right? Now if you look at that, this system under consideration is basically liquid water plus air within the container, which is kept at room temperature and pressure. Now the surroundings is the region in the vicinity of the system that is affected by this glass of water, right? Affected by the glass of water. For example, because of this glass of water, maybe the surrounding is slightly means going towards the temperature which is like the same temperature as water and all, and so it is definitely going to be affected. Means that this is the region in the vicinity of this glass of water. That's the surroundings. Now you have this air column which contains water vapor, right? This air column will contain some water vapor that is in equilibrium with water in the container, right? That's what is going to happen. This system is called closed system because it can only exchange energy, right? There can be flow of heat, right? Say for example, the surroundings is hotter than this glass of water which is kept at room temperature, then it will flow from the surroundings into this glass of water, right? That is permeable, right? Or if outside is at so that is this is one possibility. Another possibility is that heat is basically extracted out from the system by the surroundings, right? It is extracted out by the surroundings, right? All these are possible, or heat is input from the surroundings to the system. So it's like heat flux happening from water, means there is a heat transfer happening from this water container to outside, which is permitted, right? Or from outside into water, that's also permitted. So energy can always be transferred. However, you cannot, because it's closed, right? It is closed with a lid. The lid, water cannot evaporate, right? Water has this air column. The air column cannot escape. So all of these cannot happen. So there is no transfer of matter through the walls of this container, but because it's covered with a lid and all, but it can exchange energy with the surroundings. So this is called a closed system. Now, say for example, as I told you, the properties of the system in the container was like 25 degrees Celsius up to 19 Kelvin, pressure was 1 atmosphere, and say the volume was 1 liter, right? So in 1 liter we had, let's say, like 0.8 liters of water and 0.2 liters of air. Now, only thing that will influence so temperature was 25 degrees Celsius, and say outside the temperature was 30 degrees Celsius. Then this water we can get warm, and then can adjust, and somehow it can find a balance where the water inside the container and the surrounding can be at the same temperature, right? So that's possible. Now, if I remove the lid of this container, and I allow, then what happens? I allow exchange of matter and energy with the surroundings. Now I have T was 25 degrees Celsius, P was 1 atmosphere, P was 1 liter, and chemical components is like 0.8 liters of water and 0.2 liters of air. Now what I did, I took this container, okay, which is open because the lid is removed, and I put it in a hot plate, right? We just kept at say some 60 degrees Celsius. What will happen? What happens to the open system? The temperature inside the container will start increasing until it reaches 60 degrees, and water will start evaporating, right? It's not going to boil, but it is going to evaporate. There will be some evaporation, right? So temperature surroundings so will also increase to, this will equilibrate at 60 degrees Celsius. The water will have like a temperature of 60 degrees Celsius. There will be some evaporation, and after some time, after a long time, say from few days or maybe 1 or 2 days, I see that the chemical composition now what is there right inside the container is like 0.5 liters of water and 0.5 liters of air. That means 0.3 liters of water have evaporated, right? That is possible, right? So this is something that we will see in case of open system. So open system allows the transfer of matter and energy. There is yet another system which is called an isolated system. So think of a thermoflask. Thermos flask, you have seen a lot of us use thermos, right? In hot weather we use thermos to keep our water cold, and in cold weather we often carry tea or coffee, the thermos flask, right? Even hot water, right? Sometimes people carry warm water in thermos flask, right? Now, say for example, in a very hot summer day in Hyderabad, I have kept this thermos flask, filled this thermos flask with cold water at 15 degrees Celsius and 1 atmosphere pressure. Now I go to my office and I see that it is still cold, and I can enjoy this cool water, right, when I am drinking. So why is it cold? Because in a hot weather in Hyderabad, the temperature goes up to like 40 degrees Celsius, right? So why is it that this water inside this thermos, sealed thermos flask, remains at 15 degrees? This is because you have a vacuum, right? There is a vacuum in thermos. There is a good technology. There is a very nice technology here. So you have a vacuum seal and also a silver lining, so that you can prevent heat loss by radiation. And this vacuum basically does not allow any heat loss by conduction. So basically, it's vacuum sealed with a silver lining, and therefore it does not allow any exchange of heat energy. Right? It does not allow any exchange of heat energy between the system. System is the thermos, right? The water inside the thermos and the surroundings, right? Water inside the thermos cannot interact with the surroundings. So as a result, it remains at 15 degrees Celsius. It remains isolated from the surroundings, and it's closed, right? This thermos flask we keep it closed unless and means if we drink water, we will remove the lid and we'll drink. But other than that, by the way, and this exact time when you are drinking basically is the time when there will be some exchange of energy and exchange of matter, right? But other than that, as long as you are keeping this water intact there and it is sealed and there is a lid that is given, if the cap is closed, there is no exchange of matter or energy whatsoever. So as a result, so basically this vacuum seal with silver lining, it does not allow exchange of heat energy, and again it is also closed, so it does not means, right, there is a lid and it is closed and all, so it does not allow any exchange of matter. So with the surrounding, so as a result, by the way, there were earthen pots previously where we used to store water, and these earthen pots, there is like there will be pores in certain pots, and you will see that this water is evaporating, and you will see a very interesting thing. This evaporation causes cooling, right? That is the principle. So you will see that the water inside the certain pots will be like quite cool, and in fact this is something that I will ask later, that why does that happen and what is this type of system. So we will often have these questions like, what type of system is it? Is it an isolated system? Is it a closed system? Is it a open system, right? So open system means it allows for transfer of energy, it allows for transfer of matter, right? It allows for transfer of energy as well as matter. When it's a closed system, it only allows transfer of energy between the system and surroundings, right? But it does not allow transfer of matter, right? And finally, you also have this isolated system where the wall is such that it does not allow the wall, basically this vacuum seal with silver line coated with silver. This wall basically does not allow an exchange of energy between the system and the surroundings. It does not also this seal that is there all over. It does not allow exchange of matter with the surroundings. So this is called an isolated. So these systems are called isolated systems. So this is an isolated. So as I told you, it's like open system, then you have this closed system which has this leg, and then there is this isolated system. It does not allow the matter energy, right? And now you have these different types of walls. Like for example, if I have an adiabatic wall, which is that thermos flask wall, basically it does not allow exchange of heat energy between the system and the surroundings, right? Now, the opposite of adiabatic will be diathermal. Diathermal allows heat transfer between the system and the surroundings. Similarly, I can have matter transfer between the system and the surroundings if the wall is permeable. However, if it is impermeable, it does not allow, like for example, I have closed with an impermeable lid, the container is impermeable, everything is impermeable, then it does not allow flow of matter between the system and the surroundings, right? That is called impermeable. Now, if it is permeable membrane, that we have the wall is like a permeable, the wall is permeable, for example, the body of earthen pitcher. So those are permeable, so it allows water to escape, right? So basically, it allows matter to transfer or flow from system to surroundings or surroundings to system, right? And then there is also another part that we are looking at mechanical work. Say, think of mechanical work. When we think of mechanical work, we think of a piston, we think of a container, and we think of like moving the piston down or taking the piston up, right? We think of such a setting, right? In such cases, say for example, the wall is rigid. If a system is there whose wall is rigid, then the rigid wall will not allow flow of mechanical work between the system and the surroundings. The same idea happens if I have, say we are talking about system and surroundings, but I can think of like two subsystems or a composite system which contains of many subsystems which is separated by these different types of walls, right? And we can look at these walls, we can relax some conditions, we can make these walls adiabatic or diathermal, we can think of these walls to be permeable, we can make them more impermeable, we can also make these walls rigid. Rigid means it does not allow any readjustment of volume, it does not allow any flow of mechanical work between the surroundings. On the other hand, if it is flexible, then it is movable, which is basically opposite of rigid, then your piston can go down or go up, and as a result, basically you can perform mechanical work on the system. Okay, when the system walls are when the walls between the system and surroundings are flexible. Right, so we will now discuss a little bit about the mechanical work. Right, in mechanical work, basically, as we know, work is nothing but force times displacement, and force is a vector and displacement is also a vector, and if I take a dot product of it, what I get is 1, right, delta W. Right, if I do as displacement an infinitesimal or differential displacement dx, and I have a force, then F times dx is delta W. Right, it's again a differential, but it's an inexact differential. Right, and the sign convention, what we told, is work done by the surroundings on the system is positive. Right, now if you think of this, let's think of this piston. So you have this external pressure. Remember, the pressure that you are exerting, okay, is in a process. The process that you are applying is like you are exerting pressure in such a way that it's almost like a quasi-static increment of pressure. So every time you apply pressure, you allow the piston to equilibrate so that the internal pressure and the external pressure equilibrates, and again you increase the external pressure by an infinitesimal amount. That's what you are doing. Now if you see, if I am considering this external pressure, then what is happening? If you initially now I had an external pressure, and say for example my volume is changing in such a way that delta V is negative. That means my initial volume was Vi, and my final volume is like Vf. Then basically Vf is less than Vi. That means Vf minus Vi or delta V is less than 0. Now in that case, work done on the system, say you are applying pressure, right? As a result, your volume is decreasing or reducing. Now volume dV is negative. Now if dV is negative, I have to put a minus in front of P, so that minus P dV becomes positive, right? Because dV itself is negative. So if I put a minus sign, then my sign convention works, right? Minus P dV. Now some people write, say, du equals to delta Q minus delta W. In their case, they are telling delta Q, that is heat input, is positive, but delta work done by the system is positive, work done on the system is not. Right? If work done by the system is positive, now think of this. There is this internal pressure. There is this internal pressure. Now this internal pressure is increasing the volume because it is acting against the external pressure. It is increasing the volume from, say, Vf to Vi. So delta means basically, if we are looking at the internal pressure which is doing work on the surroundings, then basically we are trying to move the piston such that delta V is positive. If delta V is positive but minus delta W, so it is minus delta W, right? That's because work done by the system is positive, work done on the system is negative. Now work done by the system has to be positive. Now if work done by the system has to be positive, if delta V is positive, then P has to be positive, right? So basically here also, if I have to write delta W, in this case, where we have this different convention, it will be basically given by P dV. Here it will be given by minus P dV, right? So ultimately, when I write P dV, then my du is delta Q minus delta W. But the way we have written it is like du equals to delta Q plus delta W. And delta W in our case also, because the volume is decreasing, which is delta V is negative, so minus, so you have to put minus in front of P external, right? So to make the work done positive. So this will be delta Q minus P, right? So this is that. Now again, dV, that means volume, where dV is also an exact differential. So volume is a state function, right? Volume is a state function because dV is an exact differential. So as you can see in the differential form, the first law for a closed system can be written as du equals to delta q plus delta w plus delta w prime, right? And as you can see, delta w is f dx, which is basically f by a into a dx. A dx is nothing but the dv, right? A dx is change in volume, and there is a minus p dv because delta w has to be positive according to our sign convention. On the system has to be positive. Now remember, when this type of experiment is going on that we are doing mechanical work, this external pressure is adjusted in such a way that the process remains static and it remains the same as the internal pressure. Means every time I am incrementing the external pressure, there is an increase in there is an increment in the external pressure by a small amount. We allow the system to equilibrate in such a way locally that it has to remain the same as the internal pressure, right? In such a case, the work that we are doing, it's a very infinitesimal process. I am pressing the piston and then I am holding it. So basically, I'll give an example here. So my drawing is not that great, but I can still tell you the idea. So you have this chamber is fitted with a piston. So just make this chamber. Right, and then it is fitted with a piston, right? It is fitted with a piston. We have this chamber, and what we are doing is I put a small container, and I have also put another small container here. In this container, I have kept a lot of pebbles, right? I have kept a lot of stones, some pebbles, right? Small stones, and here I have kept nothing. Now what I am doing is I am taking one pebble and putting it here. As soon as I put one pebble here, there is a small external pressure that happens, right? There is a like I am adding some there is a P plus P. Now for one pebble. Now once it happens so slowly that the internal pressure exactly becomes like P plus P, right? It's almost like equilibrium at each step. Again I put the second pebble, and so on and so forth. Now this is one experiment that I am thinking of. Another is, instead of doing that, I take all of these pebbles. Right? I have like all of these pebbles. I put all of them together. Then what will happen? Suddenly the pressure will go up. It will not allow to equilibrate. Right? Suddenly the pressure will increase. Right? Say P plus some increase like delta P. Now you are not giving time. You have put all the pebbles together, so you are not giving time for the internal pressure to adjust, right? Internal pressure to equilibrate with the external pressure. So basically, there will be some sort of a shaking motion, right? So it will be like a to and fro motion of this piston. So it will be like it will shake, and then it will also shake about its mean positions. It will go on doing that. It will like vibrate about its mean, and then finally it will settle to that increased pressure. By the time it will settle, maybe the internal pressure also will be equal, but in the process, in the intermediate times, you will basically see that this entire piston is like going up and down. It's like vibrating about its mean, and it's like wobbling. And at that point, so there is some sort of a disturbance that you can easily feel, and that's a non-equilibrium process. On the other hand, or irreversible process, right? you put all the pebbles together, you have suddenly increased the pressure, and as a result the piston is going down. But when it is coming down, it is coming with some jerks, right? It is coming with some jerks. It is basically trying to vibrate about its mean and then finally settle down to its final position. On the other hand, the other experiment where we put these pebbles one by one, when I am putting pebbles one by one, then every time there is a small increment in pressure, there is enough time is given to the internal pressure to readjust, so that the small increment in pressure from the external can be exactly countered by the increase in the internal pressure, right? That's the so if you feel this, so it's like pebbles, and you have this plunger of the piston, and you have on the plunger you have this empty container. So pebbles put one by one, so it's like quasi-static, and the process is reversible, because again if I put it one by one, then slowly the piston head will increase, right? The volume will expand, right? That is like putting it one by one or removing it one by one. So we have a quasi-static and reversible process, because we are allowing enough time for the system to adjust the internal pressure, so that can counter the rise in external pressure, right? So that's the thing. So it is adjusted in such a way, it's like you are doing like P plus Tp type of an experiment, right? So it is always remaining the same as the internal pressure, right? That means the work done in this case is reversible. Reversible processes are these are theoretical, right? These are infinitesimally slow or quasi-static. That is, bodies or valves will never accelerate, right? They will come so slowly that you will feel like it's always static. It's almost always static. That's what it is. So what does thermodynamic equilibrium mean? Very simply, this means, say for example, I can take the example of mechanical equilibrium. Mechanical equilibrium means, if I have mechanical equilibrium, that means the sum of forces on that particular body, right? If a body is in mechanical equilibrium with the surroundings, so basically there will be no net force on the body, right? All the net forces are not, right? So a reversible process. So if that means the piston, although it is slowly, there is some slow increment at each step, there is a thermodynamic equilibrium that is achieved, and that thermodynamic equilibrium is nothing but mechanical equilibrium, which tells that the net force on the piston head is zero, right? So as I told, at each small increment of external pressure P external plus P, right? At each small increment P external plus P, the system is allowed to come to equilibrium or mechanical equilibrium such that the internal pressure is equal to the external pressure. That's the idea, right? Now again, delta W is a path function. We have already discussed this, and you can take different paths. Say for example, I can go from I to, say for example, I can go from I to B to F, or I can go from I to F directly to an okay. So I to B is an isochoric process where the volume is constant, and then pressure changes from P1 to P2. Then there is V to right? P to F is like pressure is not changing, right? So in the isochoric process, pressure is changing from P1 to P2, right? It's decreasing, and then you go from V to F where the volume is expanding at constant pressure of P2, right? Now if I look at the work done in this case, it is minus P dV and integral from V1 to V2, right? It's like that. It is at constant pressure, we are telling it is happening from V1 to V2 at constant pressure. Now, if it is constant pressure, so say for example, V2F is an isobaric process, and since it is an isobaric process, that means basically the P2 is constant, and as a result, you can easily integrate, because you can take out P from this integral, right? P, because P2 is a constant, and W just becomes minus P2 times the integral of dV from V1 to V2, right? So this is like minus P2 V2 minus V2. So it becomes very easy, right? Because the external pressure is not there. Now in an isochoric process, when there is no volume change, basically, which is W equals minus P dV, dV equal to 0. So for isochronic process, work done equal to 0. Now, if we are thinking of an isothermal process where work done, for example, PV equal to K, and if we are looking at, say, for example, 1 mole of ideal gas, then PV equals to nRT becomes just PV equals to T. Right, and T is a constant, which is an isothermal condition, and right, T is constant means it's an isothermal condition. In this case, I am integrating C from 1 to 2, and I am using W equals to, or delta W means like you can use this delta W or just W equal to minus 1 to 2 PdV, and P is basically PdV is constant, that means PV is constant. So basically, and we can tell PV equals to K. So if that is so, then P is basically K by V. So as you can see here, so minus K and by V, so dV by V is ln V. And then again there is an integral from 1 to 2, so it is like minus K ln V by V, right? And K is nothing but, you can write K, so you have this state where you have P1 here, you have P1 here, you have P1 here, and say you have right? So it becomes like minus P1 V1 ln V2 by V1. So again, if it's a polytropic process, it's like PV to the power n equals to constant. Then basically, then you can find out what's the work done. Again, you have to do this integral minus PV, and you can use this relation like it's like constant by Vn, and then you can try to do the integral. Now, consider a very interesting problem of free expansion of an ideal gas. So, if you have an ideal, so you have an ideal gas. So, this is the state 1. So, if you look at the state 1, you have an ideal gas at temperature T1, pressure P1, volume V1, and the other side of this composite system. So, this is a composite system. See, this has one system 1, another system 2, right? So, these are like two subsystems of a full composite system, which is separated by a wall. The wall is such that the gas, initially the wall is such that the gas cannot pass through, right? The gas cannot pass through the wall, right? It is impermeable. And we have maintained the right side to be empty. That means basically it is vacuum, right? Means it's like there is a vacuum inside, and it's empty. Now, if you look at the intermediate state, if I create a small orifice or an opening, immediately the gas will start filling up the empty chamber. And finally, you will achieve this state 2, where your pressure has readjusted such that pressure is all over the same. The temperature is readjusted to T1, and everywhere you have basically the same gas, right? So basically the gas has just without any pressure whatsoever from outside, the gas has just completely filled the entire chamber, right? In the entire chamber. So now in the entire chamber at every point the temperature is T1, the pressure is P2, right? But what will be, can you tell me what will be the work done? I can give you a hint. The work done in this process, because it's a free expansion, there is no pressure which is acting on the membrane or which is acting against the membrane. So pressure basically is 0. So it equal PdV, as you know. So basically work done will be 0. Now if the work done is 0, what will be delta U? Please find out. Right? The same free expansion experiment was performed by Joule. Right? It's also called Joule expansion. Right? Where you have a gas and you had vacuum on the other side of the chamber, and finally the volume of each chamber is like V naught, and there is no restriction to the expansion. And what happens is, as soon as you release this valve, you have PF on both sides, and then you have the final volume, right? So the final volume can be like, will be like, so you had Vi equal to V0 and vacuum, but now it will be like the Vf will be like 2V0, right? So it will be like the total volume will be 2V. Now there are different types of works, like for example we are talking about expansion or contraction, right? Expansion is basically like minus p dV or PdV, right, which is like internal pressure working on the surroundings. And then you can have surface expansion, right, where gamma is the surface area, and this big guy, this gamma is the surface area, and this one, the small gamma, is the surface tension. So it is like gamma d. So this is also, I think, capital gamma. You can check that. So basically, if you have a force, let's call F a generalized force. It can be a chemical driving force, it can be a surface tension force, or it can be an expansion or whatever, like mechanical expansion or mechanical contraction. So in all these cases, you can have a generalized force, and then you have a generalized displacement. So it is basically the way we are writing it, whatever way, like it's PdV or whatever gamma d gamma. But mainly, one thing we have to understand is that F is a generalized force, Z is a generalized displacement. So it works for any type of this will work for any type of work. So if I know what is the generalized displacement, if I know what is the generalized force, I can include many different types of work, including electrical work, including some magnetic work and all that stuff, right? So okay then. So today's lecture is so I hope that you have enjoyed the lecture, and if you have any questions or doubts, please feel free to post and send my TA and us emails.